Look closely at a modern computer chip, past the intricate maze of metallic wiring, and you will eventually reach the deepest layer of the architecture. This is the silicon-oxide boundary inside a single transistor. It is a microscopic, high-stress interface where the rigid silicon lattice meets an insulating layer of oxide. During manufacturing, chip makers deliberately flush this boundary with hydrogen. The hydrogen acts as a chemical cap, seeking out and tying up any unfinished dangling silicon bonds to lock the structure in place. These hydrogen caps are essential. By sealing off the rough edges of the lattice, they prevent rogue atomic defects from interfering with the precise flow of electrical charge required to make a transistor work. If that tiny hydrogen cap gets knocked loose, the remaining exposed silicon bond becomes an immediate liability. It starts trapping passing charge, nudging the transistor away from its intended electrical behavior. What registers as a major reliability problem on the scale of a server rack originates right here, a microscopic chemical patch coming loose in exactly the wrong place. In ordinary environments, this delicate boundary is constantly subjected to intense electrical and physical stress just from the normal operation of a device. For decades, the semiconductor industry assumed that the resulting wear and tear, a process they call hot carrier degradation, was essentially a thermal problem. The classical mechanics behind this assumption are straightforward. Unusually energetic charges move through the transistor, causing the surrounding atoms to heat up and shake harder over time until the bonds simply snap. Under this standard model, device degradation should follow a smooth, predictable curve, speeding up as operating temperatures rise. But recent research led by Wanchel Lee at the University of California, Santa Barbara overturns this classical model of cumulative thermal wear. The degradation does not build slowly through repeated heating collisions. Instead, the failure happens suddenly, triggered by a short-lived discrete quantum event. A single electron, striking the bond at an exact, highly specific energy level, is fully capable of severing the chemical tether on its own. By reframing electronic aging away from gradual thermal fatigue and defining it as a precise quantum interaction, engineers can now pinpoint exactly where and when failure begins inside modern devices. This graph charts the distribution of energy striking a bond. Rather than a broad wash of rising thermal stress, the danger is localized at a specific threshold, exactly 7 electronvolts. When an electron strikes with precisely 7 electronvolts of power, it briefly enters and occupies a hidden state within the silicon-hydrogen bond. This hidden state reverses the normal physics of the connection. Instead of holding the atoms together, it actively pulls the bond apart. The electron occupies this destabilizing state for only a fleeting fraction of a moment. But because the mechanics of the state are so specific, one well-placed electron hitting at 7 electron volts can cause more damage than millions of electrons colliding at other energies. This targeted energy threshold proves the fracture process is independent of the ambient temperature, completely contradicting the usual picture of heating-induced damage. Once excited by a 7 electron volt strike, the hydrogen does not simply break off and fly away like a tiny billiard ball following a clean classical path. To understand the fracture, we must represent the hydrogen atom as a quantum wave packet. It acts as a probability map of its location over time. A distinct rule is in play, a safe distance boundary extending outward from the silicon. When hit by the 7 electron volt charge, the probability cloud aggressively spreads towards that safety boundary. The condition for failure is mathematical. Rupture occurs the moment enough wave packet spread reaches beyond the threshold, even if the atom's physical center hasn't crossed the line. Applying this probability rule clarifies empirical measurements from actual devices that classical physics could never resolve. Long before this quantum mechanism was mapped, engineers observed that substituting hydrogen with deuterium significantly altered transistor lifespans. Deuterium is an isotope of hydrogen that carries an extra neutron in its nucleus, making it heavier. Early hardware tests replacing hydrogen with deuterium yielded a shift in reliability, with device lifetimes extending by factors of 10 to 50. Manufacturers recognized the heavier nucleus was responsible for the extended lifespan, but they could not determine how that extra mass was shielding the bond. The wave packet model provides the mechanical answer. The heavier nucleus physically restricts the quantum motion of the atom. Because the deuterium atom has more mass, it is harder for its probability cloud to spread outward toward the rupture threshold. By restricting that spread, the heavier nucleus effectively slows down the bond-breaking process by 100 times. The protective effect of deuterium verifies the wave packet model, allowing engineers to use the mass of a specific isotope as a design variable. Scale this mechanism up from a single bond to an entire, fully active transistor operating under a heavy computational load. High-energy electrons continually push through the thin oxide barriers, probing the interface and uncovering those hidden 7-electron-volt weak spots. Every individual connection that snaps creates a tiny, discrete structural flaw in the silicon lattice. As the transistor continues to operate, it accumulates these tiny charge-trapping defects, which gradually begin to impede the flow of electrical current. This electrical resistance slows down the chip's ability to switch on and off at the speeds required by modern software. The wave packet model provides the missing link, connecting invisible, atomic-scale probability shifts to the large-scale computational failures seen in the field. The data now aligns across 3 distinct points: the 7-electron-volt threshold, the lack of temperature dependence, and the protective mass of deuterium. Because electron-triggered bond breaking is tied to the foundational physics of the atom, these mechanics are not unique to silicon chips. This exact same analytical framework applies perfectly to analyzing radiation damage in aerospace components subjected to high-energy particle strikes. The same quantum rules map onto light-driven chemical reactions and hydrogen-linked structural defects across different classes of semiconductors. Armed with this model, material scientists can mathematically identify fragile atomic bonds before a material is physically stressed. By abandoning the classical thermal model in favor of the absolute quantum limit, manufacturers can design around hidden modes of failure before they ever reach mass production.